Okay, we're going to talk about steam generation. I'm not going to say a lot about it because the links that accompany this are really good. Let's just look at a basic set of typical steam generators. Now the very first one is one that you're fairly familiar with. It's the idea of just taking a box, heating the box and getting steam out. So I mean the original sort of heated box is going to be something like you have all used one of these, plug it into the wall, the water in here boils and you get steam out. A kettle. All good. We'll simplify that, or we'll modify that I should say, and we're going to make a continuous flow steam generator. So here's a box. We're going to get steam out. And we're going to have water in. So here's our water. Here is some kind of heat. Now in this case I'll just say, okay, it's a flame, but it could be electric, it could be some other heating process. And the heat that goes in is Q, and the amount of steam that comes out is going to depend on the water flow and the amount of energy and the size of the boiler. Boilers aren't generally built like this. Normally boilers are made to have much more powerful steam generation, much more efficient use of heat. So the most common kind of boiler that I think you'll find is what's called a fire tube boiler. Now a fire tube boiler, and as I say, I really encourage you to go online and look at the YouTubes on this because they're much better than I can draw quickly. But basically in your boiler you've got a big shell, and this is filled with water, and then through the water you've got a bunch of tubes. And then this is connected up to the firebox, and you have flames. The flame goes through the tubes and comes out the other end. And you've probably got some sort of stack here. Now of course if we build something like this and put some wheels on it, we've got our familiar steam train. Sort of a Thomas the Tank Engine type of train. We've got, for an old train like this, we've got coal, we've got a fire tube boiler, so we've got these tubes going through here, and we've got the firebox. So the coal goes into the firebox, burns, the flames go through, and it heats water, and the steam generated is collected in the steam dome, and it goes down to the pistons which drive the wheels. As I say, there's some very nice little animations and pictures in the online things that I've given you. One little comment is the chuffing sound that a steam train makes is the steam coming out of these valves, and also some steam is blown up the chimney, and this steam blowing up here sucks air and flames through the tubes. So of course if you look at a steam train you'll see the sort of chuffing effect coming out there. Anyway, the point is it's a fire tube boiler. Very, very common. You have to be careful how you use them. They generally require a license, some specific training for operating one of those boilers. Next common kind of boiler that you'd find in an industrial situation is what's called a water tube boiler. Now a water tube boiler, unlike a fire tube boiler, just simply has water flowing through a tube in the flame. So in its very simplest form you would just have something like this. So you'd have cold water coming in and you'd have steam going out. Fair enough. And then the remains of the flame would go up the stack like that. Obviously a single pipe like that's not going to be terribly useful, so in fact water tube boilers, commonly have many pipes like this. And so what you've actually got is you've got a whole lot of pipes going through. The flame comes in, goes around all the pipes and comes out, just like up there, and all those pipes are joined together, so you have water in and you have steam coming out. The important thing with a fire tube, sorry I keep calling it fire tube, with a water tube boiler is, unlike a fire tube boiler, if you have a failure you generally have a major leak and you have a great risk of an explosion. If you have a failure here, it's all inside the flame box, and even if a tube breaks, it has to burst out of the flame box like this before it becomes a problem. Whereas with a fire tube boiler, any rupture on the outside can cause a major external explosion. So these are considered to be inherently safer than these fire tube types. Reasonably common where you have a modest amount of steam. Typically if people want a lot of steam, they still stick with that type of design. And the other kind of boiler that we'll look at is an electrical boiler. I found it a bit hard to find good web pages on this. I was a bit surprised. But in its simplest term, I've drawn a slightly more complicated one here. If I have water coming in, so it's very much like that first boiler that I drew, and I've got two electrodes. So these go off to some source of electric power. Then the electricity flowing in between the electrodes heats the water. So why would you want to use it? Well, first of all, they're incredibly simple. It's just two electrodes, nothing in here. This is just showing where the electricity is flowing through the water. There's two electrodes and plug it into the power. We have a piece of apparatus called a Kjeldahl still, which has exactly that, to generate a small amount of steam for the instrument. And all that is just two electrodes, one shaped like that and one shaped like that. So it's just like a little ring, like a can sitting on top of another can, and the electricity is connected straight into the wall socket, 230 volts. I'll redraw that. The outside can and the inside can. Now why would we use it? Well, it's very small, it's only about that big, very compact, it sits inside a glass boiling chamber. But the really good thing about electric boilers like this is that if the water level drops and gets down below the electrodes, it simply stops. So if you run out of water, if there's a failure or a leak, as soon as the water level drops, it stops. So it makes them very safe in that sense. And because there's no tubes, there's nothing other than just a box with a lot of electrodes in, they're very simple, they can be very cheap. And the big ones can actually generate a lot of power. I've seen one almost the size of this building. This was in Canada, and it was used to provide a huge amount of steam for a paper mill. And it really was quite simply a series of huge boxes plugged directly into the very high voltage power coming directly from the northern Quebec power stations. Very effective. So let's look just for a second at boiler efficiency. Boiler efficiency is obviously important. If we look at the amount of heat flowing through a boiler, that's going to depend on the mass of water times the difference between the enthalpies. Now this would be the enthalpy of steam, and this would be the enthalpy of water in most cases. If we look at the fuel which is going in, this could be electricity, it could be oil, it could be gas, it could be wood, it could be anything. It's going to be equal to the mass, or in the case of oil or gas or wood, times the energy constant. This is just a number. So what it's saying is that when you burn this material, you get this amount of energy out of it. It's like a specific heat or something similar to that. So we can then say that the efficiency, and this is the nu, that's a symbol for efficiency, is the amount of heat coming out divided by the amount of heat going in. And that's equal to the mass of fuel used, how fast that's being used, times the difference between the heat in and the heat out, over the mass times the energy constant. Just looking at this to make sure we got this right. It's the mass of steam coming out. I didn't put the ms here. Now, for most fuels, they're not that flash. The typical efficiency for an oil burner is around about 80%. Now, there's a couple of other bits here. I'm going to talk about steam throttling, but I'm not going to talk about the calorimeter. So what is steam throttling? Well, if you have steam coming out of your boiler and you pass it through a little hole, so we've got some kind of blockage here, then we're going to get a drop in pressure. So as the steam's going through, it's being squeezed through the small hole, the pressure drops. The energy which is going in is going to be the same as the energy going out. So we've got this balance. We know that the energies are the same, but there's a pressure drop. So as a result, you're going to get other changes depending on what's happening. The one which we're most interested in actually is dryness. If I look at this enthalpy temperature diagram, then we've seen this before. This is when it boils. Goes up like this. Sorry, these are typically temperatures and the pressures are on these scales here. Then we remember that it's got a shape like this. And the next thing you need to remember is that as you go along from here to here, the dryness of the water changes. So it starts off being, sorry, the dryness of the steam changes. It starts off being extremely wet steam. That's about 50%. And this is 100% dry steam. Now, we normally, no matter how much you try, there's always going to be a bit of moisture in your steam unless you're going for very high temperatures and pressures. So as a result, most steam generation gives you, say, 99% dry. It doesn't give you 100% dry steam. However, you may want to dry the steam, to have dry steam, no liquid water. Or, because the enthalpies are the same and the pressures are different, you may also want to increase the volume of the steam by dropping the pressure. This would be useful if you're trying to drive some kind of machine with it. So if I generate wet steam, say here, and then pass it through a hole, a blockage in the pipe, then the pressure is going to drop, and it's going to go from this wet steam region here, it's going to drop down into this dry superheated steam region here. So this does two things. First, it dries the steam, and the second thing, by dropping the pressure, it expands. And this combination of dried, expanded steam is called flash steam. So that's all we're going to say about that. Flash steam has its uses either for driving machines or where you want really good dry steam.